Okay, so we want to look at the connection between Taylor polynomials and transcendental functions, or even other polynomial functions for that matter, because we're just learning how to work with these today. So we have explored y equals e to the x with Desmos, and now I want to actually go back and look at some of these functional values that we were working with before. So let's pick a value close to 0, 1. So that's the whole premise of this. So let's say x is 0.1, so it's just a little bit to the right of 0. Well, what happens to that x value on these different curves? So if I go down here and I compare the function g at 0.1 with f of 0.1, we can see that we're a little bit far off. So g of 0.1 ends up being 1. So that's not very close at all. Well, what if I use that next function? So what if I use the h of x function? Remember that got a little bit closer? So what if I find h of 1? Well, now I'm at 1.1. So I'm getting a little bit closer to what the functionals, or the actual functional value would have been at y equal e to the x. What if I go to the function j? Let's get it up here first. So we know j is following a little bit closer. So what happens if I substitute 0.1 into my function j? I'm getting a little closer, 1.105. And if I use the function k, (1.10516), and the 6 is repeating. So 1.10516. So I'm getting ever so close. And finally, if I use the function p, I end up with something really close, right? I am 1, 2, 3, 4, 5 decimal places out. That's really close. If I were using this in science and I was trying to formulate a vaccine, that would probably be close enough that I'm not going to kill anybody, right? If I'm making a part for a car, that would be close enough that the part's not going to degrade over time. It's going to serve its purpose. So 1.10517. So notice there is a pattern to these polynomials that I'm using. And the one before has a repetition in the next one. So I can see h of x in the first two terms of j of x. And I can see j of x in the first three terms of k of x. And I can see k of x in the first three terms of this last polynomial. So to get closer and closer, I'm just changing that polynomial by changing the final term. And the pattern that we're following is called a Taylor polynomial. So we can either represent it with summation notation, which is what is used here. So with summation notation, you let the value of n go up by 1. So we would let n be 0, and then we would let it be 1, and then 2, and then 3, and then 4, and so on, until we get as many terms in our polynomial that we want. When we're building this polynomial, the n on the f means the derivative. So f n of a means the derivative. So it's either the first derivative, the second derivative, the third, the fourth, and so on. F of 0 would mean just the function. N factorial is an operation in math that we use when we're counting. And that means every number from that value down to 1 multiplied together. So for example, 6 factorial would mean 6 times 5 times 4 times 3 times 2 times 1. 9 factorial would be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that ends up coming into that equation when we're building our coefficient of x. With your calculators, you can find the factorial in 2 different ways. The way that I know to find it is there is a math key. So you either use alpha and F2 and then move over to probability and down, or there's a shortcut. And I don't ever remember the shortcut, but I found a YouTube video that has the shortcut, and I have given you access to that, so you can go watch that video as well. Our book chooses to go ahead and use a series to show what every step would be. And I have this small here so that as I do one of these, you can see where I am deriving these values. Remember, this is taken from your text, so you can go there in section 11.1 and see it as well. All right, so we just want to get the formula. So what are they saying? What does that formula look like if I want the first polynomial? So the first Taylor polynomial, if I center it at 0, would simply be to take f of 0 and then add the first derivative, evaluated at 0, multiplied by the polynomial factor to the first. So P1, everything's to the first. First derivative and x minus 1 to the first. That's where you want to stop. For the second Taylor polynomial, you repeat the first one and then you add one more term. So you're going to have f of 0 plus f prime of 0 times x minus a plus the second derivative, evaluated at 0, and then here's where it changes, divided by 2 factorial times x minus a. Oh, and you know what? And we're doing this at 0. So let me back this out. I meant to do that there. And we were finding this one at 0, so we won't have x minus a. Yes, I'll try and clean that up. So the first derivative times x, actually, I don't even need the parentheses on that, plus the second derivative, evaluated at 0, because remember we're doing this at 0, divided by 2 factorial times x squared, because x minus a, if a is 0, that'd just be x. Notice on the first polynomial, I didn't divide it by 1 factorial, because what is 1 factorial? 1. And now the third polynomial would be the functional value at 0 plus the first derivative, evaluated at 0 times x, plus the second derivative, evaluated at 0, divided by 2 factorial times x squared, and then we're going to add one more term. The third derivative, evaluated at 0, divided by 3 factorial times x cubed. So let's see if we could come up with those polynomials that were being used in my Desmo exploration. So this is the pattern for the Taylor polynomial that we're going to follow. And if I were doing these I would probably make this chart to help as we go through the process. So our function is e to the x. What's the first derivative? What's the second derivative? What's the third derivative? E to the x, right? And when I evaluate those at 0, I'm going to get the same value as well. So e to the 0th is 1. It's 1, it's 1, it's 1. So to get the first polynomial, remember I take the functional value at 0, so that's 1. And then I add to that the first derivative evaluated at 0 times x, so that's 1 plus x. For the next one, I would recopy the first polynomial, 1 plus x, and I would add to that the next term, which would be the second derivative, so that's 1, divided by 2 factorial, and 2 times 1 would be 2, and then x to the second. And then for the third polynomial, I would recopy the second polynomial, and I would add one more term. And that term is the value of the third derivative evaluated where we're going to look. This is called a neighborhood close to x equals 0, divided by 3 factorial. Well, 3 factorial would be 3 times 2 times 1, and so that's 6 x to the third. So let's go back up and compare. And sure enough, those are the polynomials I was using. Okay,